Volumes of Other Cross-Sections, Part 2. In Part 1, we looked at a region that was the base of a solid coming out of your screen or out of your paper, where cross-sections perpendicular to the x-axis were shapes that were typical geometric shapes. We found the volume of one of those cross-sections, then added them all together to find the entire volume of the shape. So for a reminder, if our cross-sections are squares, then the volume would be base squared times dx, where b, the base, is that length, and dx is the very small width of the cross-section. For isosceles right triangles, where the leg was the base, the volume of one cross-section was 1/2 of a square times dx. For an isosceles right triangle, whose hypotenuse was the base, the volume of one cross-section was 1/4 of a square times dx. For the equilateral triangle, the volume was √3/4 base squared times dx. And finally, for the semicircle, the volume was π/8 base squared times dx. Certainly there are other shapes, but we stick mainly to those and rectangles, which I'll do an example of down below. So let's look at this first example. Consider the region bounded by the x-axis and the graph f of x equals 2x minus x squared. Imagine that the shape is coming out of the screen, and if I were to slice down through it, I would make cross sections. And let's say for the first one that the cross section coming out of the screen is a square with a small width of dx. So I know that the volume is the sum of all my squares that have a tiny width of dx. We're missing the limits, so we need to find the x-intercepts. That's pretty easy to do. We will simply set the function equal to 0. And then we will factor out an x. Now, you could have done this just by guessing and checking, I'm supposing, but I wanted to show the algebra. So the volume would be the integral from 0 to 2 of b squared dx. Let's do the algebra of this one. I'm going to start by putting in my base into the integrand. We'll square it as such. Before I find the antiderivative, we really need to multiply out the inner part. So I get 2x quantity squared minus 4x cubes plus x to the 4th dx. Now we're just doing power rules and constant rules. So I'll find the antiderivatives of each piece. As such. Then we can plug in the top limit. So I can plug in the 2. I get 4/3 times 2 cubed minus 2 to the 4th plus 2 to the 5th over 5. Subtract the bottom limit. We don't really need to because it's 0, but I'll put it there anyways. And then, as normal, simplify as desired. So these were the squares. What if instead of squares coming out of the screen, they were semicircles. Then the volume is pi over 8 times the integral of b squared dx. And we don't really need to do much work because I did enough in the previous part. So it's simply pi over 8 times the volume you get when you use squares. We'll take a look at one more example in this video. And to do the integral, you'll need to use integration by parts. So if you haven't done integration by parts yet, don't worry. I just wanted to do an integral with an advanced technique. But let's look at the region bounded by the y-axis and the graphs of cosine of x and sine of x. So it's going to be this part right there on your screen. We're going to have cross sections perpendicular to the x-axis, like such, so a tiny width of delta x. They're coming out of the board or out of the screen, and each rectangle will have a height of x. Well, the area of any rectangle is base times height. If we multiply by dx, we get a volume. So let's take a look at each of these pieces. So the base is going to be this length from top to bottom. That is cosine of x minus sine of x. The height is x because I say so, right here. And then the width is dx. So that's the volume of one cross section. To find the volume of the entire shape, we're going to sum all these tiny cross sections together, starting at 0 because I said that one of the boundaries is the y-axis. And then the upper limit is pi over 4, because that's the first place in the first quadrant where cosine and sine have the same value. So now we're going to use integration by parts to solve this one. And if you don't know the technique, you can set it up but not solve, and you would probably be done. But if you know integration by parts, let's continue. This is the way I do it. So I know that the integral of u dv is uv minus the integral of v du. So I have to set up things. I'm given this, that is, my integral is the integral of u dv, and I get to choose what I want. So I'm going to choose u to be x, and then I'm going to choose dv to be whatever is left over. In this case, cosine minus sine times dx. Now over here, I need to find v because I don't have that yet. And I need to find du because I don't have that yet. So du is simply dx. And then v is the antiderivative of dv here. So I have sine x plus cosine x. We don't need the plus c. Not when we're doing this, not at this point. So I can plug in, since I've given this side, I'm going to plug these pieces into the right side. So I have u times v minus the integral of v du. I'm leaving off my limits for now. I'll put them in at the very end. So let's continue on. I'm just going to rewrite this first part, and then I need to integrate. So the integral of negative sine is positive cosine. The integral of negative cosine is negative sine. And then now I remember my limits, so I'll plug them in at this point, from 0 to pi over 4. Finishing it off, we'll plug in the upper limit, x equals pi over 4. The sine and cosine of pi over 4 are both root 2 over 2. Plus the cosine of pi over 4 minus the sine of pi over 4. I guess I'll write it. I already know that they're going to cancel. And that is the upper limit. Now we can subtract and plug in the lower limit. I can get 0 times something, so it doesn't really matter, plus the cosine of 0 minus the sine of 0. So this part goes to 0. Let's see if we can put some things together. I have pi over 4 times 2 root 2 over 2 minus 1. And that is the volume of the shape whose base is the region bounded by the y-axis and the graphs of cosine of x and sine of x, where the cross-sections perpendicular to the x-axis are rectangles with height x.